Okay, so we're back for the part 2 of this async-await presentation, and what we're going to look at here is a few other ideas or concepts about the async-await capabilities in C#5, and then look at some scenarios where we should or can and shouldn't be using async-await or the asynchronous I/O capabilities in C#5. And then after that, we'd be looking at some load test and performance test capabilities. We'd be looking at the load test and performance test capabilities before we look at the various scenarios in which we can or cannot or should not use async I/O. And we'd be looking at, after that, some possible potential problems if you kind of extrapolate further from what we understand the async I/O gives us in terms of the scalability, then there could be potentially other kinds of problems that you may not have anticipated. And I wanted to introduce those concepts to you as well. So let's look at this last, the task one here. So in the last part, in the previous part, we looked at, we modified this get videos async method, and we used a task combinator, the when all capability, to await multiple tasks. And another scenario that you might be looking at or curious about is, what if you had to call multiple services, maybe one or more services within your either business layer or data layer, depending on where you're at, and you needed to kind of go out or fan out to multiple services, come back with a result. So let's look at that scenario. Now, the for each is kind of doing that, except it's going to one, it's considered sort of one service. But if you were to sort of unwrap this for each yourself, then you'd actually come up with something like this. You'd say, is equal to, let's do this download data async, but we'll give it a specific URL as if that were a call to one service, and we'll copy that over to make that a call to multiple services. So we got 3 tasks here, and now you could fall into the same trap. I'm just going to delete this portion here, just so that there's no, we'll leave that part here. So rather than looping through the calling a service multiple times, imagine this to be a call to 3 different services. So the trap we could fall into is we await each call, right? So again, it's kind of the same problem where you might think you're doing these 3 tasks asynchronously, and you are doing them asynchronously, except you're leaving some performance on the table because you're awaiting each task before starting the next one. And of course, because we've awaited this variable here is no longer a task, it's actually been unwrapped. So what you're seeing here really is of IEnumerable video. So you got an IEnumerable here, and this is an IEnumerable video. So keep that in mind. Again, the await is unwrapping the task. So rather than awaiting each task, what we are doing here in this scenario is we are essentially firing off 3 separate calls to 3 separate services, doing them asynchronously, so they are returning a task. A task is nothing but an operation that is going to complete in the future, something that's going to be done or returned to you with the completion, if you will, at a later point in time. And so we got these 3 tasks, and we can still do the when all. And in this case, we won't obviously we could have put them all into a list and then use the when all as it is, or we could just simply do task 1, task 2. There's a params overload here, if you can see this, that allows us to just put in n number of tasks as parameters. So we're using that option here. And so this is another way you can combine calls to multiple services, get the same benefit. So you don't have to have them sort of set up in an array or something where you have to for each them or do something of that sort. If you have 3 distinct services to call or more services to call, you can call them all asynchronously simultaneously. So in this case, they are all obviously async calls, but they're also being done simultaneously, all together, if you will. And then we do an await on all. So we're not waiting on all, we're doing an await on all. And so now there's another combinator here, that is when any. The when any returns, of course, just one of the kind, so it's only returning to us an IEnumerable of video, not an IEnumerable of IEnumerable of video, or it's actually returning a task of IEnumerable of video. But the when any is useful when you may have, in some scenarios, you might have the option to do multiple tasks asynchronously, and you are okay as soon as one of them is complete. You don't have to wait on or await on all of them. You just need to await on any one. The first one that comes back, you're ready to go, and you can sort of scrap or forget about the others that you might have had. This is a pretty common scenario when you have doing some sort of optimization, statistical optimization, etc., where you probably have various ways to get the job done, but you fire off multiple, and maybe one comes sooner than the next, and as soon as the one comes back, you're fine with whichever comes back. You're not waiting on all of them or awaiting all of them. So the when any comes in handy in those scenarios. The other thing I want to show you is, so I hope this is clear, where if you have this situation where you're calling multiple services and they're sort of independent, or maybe once you call the one and then you have to wait this one to be able to call the next two after that. So you could do this. You could say, okay, let's await the one, and as soon as this one is done, I extract the value of that and pass it into the next two calls to two other services. So these two can await the previous one, and then you can take the result of that and somehow pass it into, or a portion of the result of that, pass it into the next two. So you can have various sort of scenarios here. So in this case, I'm just doing that. The other thing is you could use link. So instead of having this whole thing with a for each, we could have just done all video tasks is equal to from URL in sources, select download data async, giving it the URL, and that's the same as the for each with the list and everything else. And you can see over here now the return type is an IEnumerable of T, where T is nothing but a task of IEnumerable of video, right? So, and once you have this all video tasks, you can still do the same thing. You can use the combinator and await on all of those tasks that when they all complete, you return the result. So this was the same as the for each with the declaration of a complex structure that had a list of tasks of IEnumerable of videos. Okay, so this I think finishes some of the sort of the ways in which you could use async, the new async IO async capabilities in C#5. Now I want to show you in the next step. Okay, so next up is to show you some of the performance load testing capabilities that we have in Visual Studio. What I'm going to do is I'm just going to back all of this stuff out, so we're not, since we're going to be using this stuff for the performance testing as well, comparing it to the synchronous version. So I'm going to leave the link version here, even though this is a for each version. I don't think it's going to be much of a difference. Performance wise, the link version is, I guess, comparable to the for each version anyways. Okay, so to this solution that we have right now, we're going to add a new test project. In this case, it's going to be a web performance test, performance and load test project. And once we have that, we have a web test. I'm just going to name this web test sync. So this is the sync web test. And let's get the URL here. Just going to copy this URLs. When we record the test in a minute, I'm going to record the URL that calls the sync action in our web application. I'm just going to let this finish here. make sure it's still working. Okay, so now let's record the test. Go to the sync URL and let's record it here. We now stop it. So at this point we've recorded a web test that is going to the URL, in this case, that we want the sync version of it. We've called it sync, and once this finishes, we'll then add to this test project a load test. Now the load tests are, I'm not going to go into the depth of it, one, because I'm not extremely familiar with this stuff, but I can explain some things, but I'm going to also skip some of the things that just to speed things up here. So I'm going to call the scenario, let's call this sync scenario, and the think time here is, you know, you're running these tests automated. So if a human being were to be sitting on your website clicking links one after the other, there would be a certain amount of time between one click and the next click. And so if you wanted to introduce the think times in there, you could have those think times included, so that you're not unnecessarily stressing your tests, your system on a test, and seeing that you're not getting the performance you expect, even though in reality human beings don't go clicking links in rapid fire succession, you know, in millisecond times. So you could add a think time here. In our specific case here, we're going to use 50 users simultaneously as a simulated load, and in this case, each of these options here, it describes what it is trying to do here. I'm just going to use the default option, which is based on the total number of tests, rather than bunches of users and stuff and various other combinations. So oops, I didn't want to do that, so let me just delete this test. I'm going to start over. Obviously it has no idea what the load test itself is at this point. So much for talking and trying to type. So I'm going to call this again sync scenario, no think time, simulate 50 users. Okay, so the next thing here is to the actual test that we want to add. So I'm going to choose the sync test, as you can see here. You could have multiple tests in a load test. In our case, because we're trying to compare the synchronous version with the asynchronous version, we're just going to be adding the one test in each of the load tests. So we'll create another load test that will test the async version. Oops, sorry. To actually add it here. Okay, next up, the bandwidths. Now, interesting anecdotal experience here I had in one of my previous jobs. I was developing a video website in the public domain, and after a while we started seeing a lot of backed up traffic, a lot of bottlenecking going on, and we immediately suspected the folks from the US with high bandwidths, because, you know, they were just downloading videos by the gazillion. And right away we said, oh, you know, we need to do something with these people, because they just completely backing up our primary servers. But before we did that, luckily we said, let's sort of do some load testing and make sure that we are in effect being able to simulate the load test, and therefore we can, whatever measures we might take, we can verify that they actually work. To cut a long story short, what really happened was we found that the requests that were coming from people with slower bandwidths, like the 56K modems, 36K modems, etc., were actually the ones that were causing the bottleneck. Because imagine somebody downloading a video on a very slow internet connection, then of course a video that would normally take somebody else, let's say 10 minutes to download, can end up taking somebody else hours. 3, 4, 8 hours to download. And now you got 3,000-4,000 people downloading these videos from slow modems. You got 3,000-4,000 requests that are being queued up, not queued up, but are being in use at any given moment in time over long periods of time, 3 hours, 5 hours, 10 hours. And those were the requests that are really causing us the trouble, not the ones that came in with a high-speed bandwidth that downloaded the video in a few minutes and disappeared, but the ones that were sticking around for much, much longer. So Sometimes just keep that in mind. What you might think is causing the problem is not necessarily the thing that causes you your problems. But in the previous thing, you could have the load test that is distributed across LAN and various other bandwidths in case you want to test that in your load test scenarios to kind of make it a lot more realistic. This scenario, in this case here, you can page, you can select again a distribution for different browsers. Maybe you got some programming in your pages or controllers where you're determining the user agent, and you got to kind of go down a different path based on the browser making the request. As I said earlier here, the load testing features in Visual Studio allow you to essentially have a load test farm that is a bunch of machines that are sort of behaving as the client machines, if you will, that then can make requests against the system under test, which could be behind a load balanced server or just a single server, depending on how you want to do your tests, but allows you to control the software here, the framework here allows you to control those other servers from a single point. So you could actually add many boxes here as your servers, and then it essentially deploys a test agent onto these boxes, and you can then make the request from those boxes while you're controlling the whole thing from here. And I'm not going to go into the details of that, but just so you have an idea, this is pretty involved stuff. I believe that you need to be a performance engineer to do a really good job of doing performance testing. A typical, no matter how good you are, software engineer is not the best person because it's a specialized skill. So you could be pretty good as a performance engineer, but essentially it should be like a full-time job for you to really get performance testing, load testing. And this tool is kind of ideal for that sort of scenario, where it allows you to go really crazy with the kinds of load tests you want to do. We'll test X number of iterations. In this case, we'll choose 1,000 iterations. So essentially we're going to be doing the synchronous call here for 1,000 iterations with 50 users simultaneously. That takes care of this test. Let me call this test the sync load test. So now that we have a sync load test, let's run it and we'll get a sense of how that works. So this is going to be calling the synchronous oops, didn't mean to actually run the test. Okay, there it is. We're running the synchronous action, if you will, for 50 users 1,000 times, right? So you can see it's already done about 2061. And these various graphs, I'll go into slight detail in these graphs, are recording different kinds of information. In this case, the page response time. You can see the response time was initially climbing. And I believe what's happened here is that once the thread pool threads have been created to support the rapid fire requests, it eventually tapers out, or not tapers out, but it flattens out to a certain consistent request response times. Each of the graphs is showing different things, and each of the graphs can be configured separately or differently as per your liking to record or monitor different kinds of counters. And there's a bunch of counters that are being recorded here, so even after the tests have run, you can graph the counters that you're interested in later on and then do comparative tests, so comparative results checking. Of course, as I said, it's pretty extensive or intensive stuff here. In order to understand what you should be testing against or comparing against, you need to really understand what it is that you are doing without sort of sending out false signals, if you will, in your performance test. So you're comparing apples to apples and not apples to oranges, and the counters you're measuring are actually counters that would make sense for the kinds of tests that you're trying to do here. This feature, as I said earlier, was introduced I definitely remember using this in VS 2010, but if I'm not mistaken, it was there before. And before that, if it wasn't this tool, there was another stress test tool that was available that I've used, which was pretty similar, not as graphical and UI driven as this is, but this was definitely there in VS 2010 as well. They probably made some improvements in 2012. So we're done with this the synchronous version of this test, and what we see is a sort of a basic summary here that tells us that for the 95% of the time we had a page time of 7 seconds, and we got about 8.25 tests per second, which should be the same as the request per second, because we only have one test in this whole load test, and so the number of pages per second was 8.25 pages per second. Going back to the graphs, the way this works is, first of all, when you select a certain counter here, the graph or the line that represents that counter gets kind of bolded, if you will, so you can see what's going on. And so you can see here the average page time went from, I guess, 3.67 to about 6.72. As the load increased, the time it took was increasing, and eventually kind of averaged out at about 5.9 pages per second. Oh, sorry, seconds per page. If you want, you can remove it from the graph, and if you want, you can add other counters. So I have this key indicators graph selected here, and I can say, okay, well, this green thing here is pages per second. That's great, but I really don't care for the users here, right? This let me click there, that one. So I can remove that, or I can just uncheck it, or I can just select it and hit the delete key. It'll be deleted. The orange one is threshold variations per second. Maybe I'm not interested in that. I can just delete that. But I'm gonna add other counters to this graph here. So if I select this graph, let's say physical disk, discrete times, average disk seconds per average disk reads per second, and if I add that for my C drive, it comes in here, and then it gets graphed as well. So you can see that one. Now these graphs also have zoom in capabilities, so you can zoom in here in case you're not able to see the details, and you can make these graphs bigger and smaller in case you want to see the more details. So that was the disk drive, the reads per second. You can see it changing, and it starts to go higher and higher because of the asynchronous capabilities. And this, in this case, is reading the images from the local drive. So there's lots of configurability here. Now what I want to do is just compare this, create another test, a load test that is using the async version, and compare that with the let me actually create the test first, which is so there's a little confusion here in the naming. At least for me, it is there's a load test and there's a web performance test. The load test is the load test we just did the graph here, and the web performance test is what we would call like the unit test for websites. So I'm going to now call the async version here and record that as a test. And once it's done, the one request here, we stop it. That now creates like what I call the unit test for this URL. I'm just going to make sure I rename the test after this is done to asynchronous. And then we'll associate this unit test, web unit test, to load test. So we'll call this async test or async. And then let's add a load test. This time, let's call the scenario the async scenario for 50 simultaneous users. Oops, made a mistake again. There's ways to edit it, but I'll just spend time trying to figure that out. So let me just delete this. Which one is it? Yeah, so let me delete this load test and create a new one. Async scenario. I don't know why it does that. It leaves the focus on the finish after a while. Okay, so now over here I'm going to add the async test, right, to the load test. And in this page here, you're able to choose. You can distribute within the full tests. In this case, we're going to do the same 1,000 iterations for 50 users. You could distribute some of them to be the LAN, some of them to be different speeds, as I mentioned earlier. Okay, so here we want to change this to 100,000 iterations as we did the last one. Okay, so now I'm going to run this load test. Let's also call this the async load test, async load. Okay. Now we're going to run this 1,000 times for 50 simultaneous users, and then we'll compare the results of those two. So I'm going to pause here, wait for this to finish, and then I'll resume the recording once we're done with these tests. So you don't have to wait. Okay, so we're back with the asynchronous version or asynchronous load test that's been done here, and let's compare the synchronous version with the asynchronous version. You can see here just a high-level comparison here. We're going to look at the number of requests per second. That is 132 for the synchronous version. Let's look at the same for the asynchronous version. Requests per second, 140. So you can see that there's a few more requests per second here between the synchronous and the asynchronous version. And if you look at the number of pages per second, yes, pages per second, 8.25 pages per second is the synchronous version, and the asynchronous version is 8.44. So not a big margin of difference here, but unless I've made some mistakes in the code here, normally I see a much bigger difference between synchronous and the asynchronous versions, almost twice as fast or twice as scalable, if you will. But on this machine, maybe things are slightly different. So again, because we're doing the performance tests on the same machine and the clients are on the same machine, the system under load is on the same machine, some of the test results can be skewed quite a bit. So, again, you have to know how to test and you have to know what you want to test. On some machines that are, I guess, faster, where the disk IOs are faster, I found that the test results are quite a bit different, the difference between the async and the synchronous version. So anyway, that was the moving on. That is the demonstration of how to do load testing with some of the tools that are available to you in Visual Studio. And let's move back to the presentations. So we were at our show me the code, and the next slide up here. So just another recap. A task represents an ongoing operation. So when you have a task in hand, all it's saying is that there's possibly an ongoing operation, and you can await it. In this case, if it's an asynchronous IO task, you can await it, and when it completes, you will have the result of that task in your hands. Async methods need to be marked with the async modifier. Let me get my... So the async modifier, as you're aware, something we've been doing all along, is marking our methods with the async modifier. Async methods must return either a task of T or a task. The void return is allowed by the compiler. I believe the void returning is primarily for support of events. So you could have a button click event, if you will, that you want to now convert into asynchronous. So you're going to have to modify it with the async modifier. But events in .NET always return a void, and so rather than having to return a task of something, the void is allowed to support now events to be made asynchronous. So remember, the asynchronous thing goes from end to end, meaning from the point of entry or the point of starting to all the way to the end and back. So if you have a button click event that needs to start off an asynchronous process, then the button click event needs to be marked with the async modifier to then call into another method that is also asynchronous. And that's why this void returning is supported, I believe, in .NET, in C#. You must use the await contextual keyword somewhere in an async or in a method marked with the async modifier. So just because you marked a method with the async modifier doesn't make it asynchronous unless there is at least one call that has the await contextual keyword in front of it. The async methods are resumed when an awaited operation completes, which means that it's almost like re-entering code. And I think I'll show you in an example later using iterators, so you kind of get a sense of what I'm talking about here. when the execution encounters an await keyword, it essentially leaves that method. Execution leaves the method, and it returns when the awaited operation completes. So it is resumed or re-entering. It looks like it's re-entering code, but it's essentially just resumed after the await. So from an execution standpoint, even though the debugging experience, as I showed in the last part, the debugging experience is almost identical, if not identical, to the synchronous versions of a style of writing code, and the way you would expect the debugger to behave behind the scenes is actually leaving execution from that method and then re-entering or resuming where it left off. Now now let's look at the iterator thing that I was talking about earlier, where I think it's pretty interesting to get a sense of how the await async-await stuff was sort of implemented, very similar to the iterators. So I'm going to start a new application here, and I'm just going to create a iterator, or define a method that is a iterator. So I'm not going to create an iterator, but just have a method. Let's have this method return an enumerable of integers, and let's call this get numbers. And the way I'm going to implement this is I'm going to do a yield return 1. If you've not used this before, you'll find this pretty fascinating. Yield return 2. So this is just standard iterator stuff, but I know a lot of people haven't used this sort of thing. Okay, so that's my method get numbers, and over here I can for each over this, right? So it's a standard for each thing, and you could write out the number to the console, and that's how you would use it. Now let's debug this to see how this actually works. The interesting thing is and this is similar to how the await keyword works. In other words, instead of yield, if you can imagine this to be await, let's take a look at. So I put a breakpoint right in the beginning of this this method, and I'm going to hit the F5 key to run. So for the first time, as in while it's iterating over the numbers thing here, it comes in this method, and I'm going to step. Oops, actually I can't do the keyboard steps. So right, so I step in here. Actually, let me step into just to make sure we go back out, so you can see it coming back into this method here. Okay, so yield return 1, and as soon as I execute yield return 1, it actually goes back out to the calling method, in this case the main method here. Oh, what happened? Okay, let me run this again. I thought I hit the step. Oh, step out. Okay, so it comes in here, right, and writes to the console. Now of course when you do when it loops around to the for each again, it's going to come back. I'm not sure what that's why it's doing that. Anyway, let me just do it again. So steps in here, and it exists from this method, goes back up there, right, and then it comes back, loops around. What's going to happen here? Now I've got a breakpoint here, right, but it never came in here, yet it's gone past. So what's happening is it's re-entering, if you will, or is resuming this method each time. Okay, now it's going to come back to yield return 3. See, it didn't stop here, it didn't stop there, it just came back here where it left off from the previous step. So I'm just going to do this again so you see it all working correctly. Okay, so I'm going to F10. So it comes in here, goes back out, goes into the loop, writes it to the console, loops around, comes back to get the next number, and it just jumps straight to yield return 2. In other words, it re-enters, if you will, or resumes this method where it left off. That's what it appears like. It's obviously not doing that. It's not re-entering code, but that's what it looks like, and that's exactly how the yield return is behaving. Even though it doesn't appear to be doing that, it actually exits every time it hits the await keyword. My mistake. Every time it hits the await keyword, execution leaves the method, and then it resumes when the awaited method completes, right? Because asynchronous. It's kind of like the yield return. So I hope this actually explains it. This is how in my head, I keep this mental model of the await, as in when I see an await in my code, I know it's going to be leaving and coming back or resuming the method, even though when I debug it, it seems to be synchronous. So just wanted to show you guys something that works similar to that. In this case, the iterators are introduced in .NET 2. You can await anything that implements the awaiter pattern. We have not looked at the awaiter pattern here. It's not something, well, personally, I've not done anything. I don't see the need for it. But again, this stuff is so new in C# that probably some of the patterns of usage have not been exercised yet. But they do support anything that implements the awaiter pattern. Essentially, something that implements the getAwaiter method or has a method called getAwaiter on it, and that becomes the awaiter pattern. But for the most part, you'll be using the sort of the .NET methods that end with the async keyword, or in some cases because of naming conflicts, meaning methods that were already ending with the word async prior to .NET C#5. They now have task async as the ending. So if you either see an async method, a method ending with the word async in it, or task async, they are awaitable methods, and you would be using those. Typically, again, all of the I/O stuff, streams, sockets, files, stuff like that. Databases. Or ADO.NET, using ADO.NET Core, the core ADO.NET functionality. Some guidance: don't mix the paradigms of blocking and async. As we saw earlier in the code samples, there were some methods that did the blocking call with the .result method. You don't want to mix those two. In fact, if you did, you get kind of unpredictable results. Typically, system just kind of hangs. It doesn't ever come back in some cases, or in most cases. Remember that asynchrony is not a performance optimization for the individual operations, but rather a performance as a whole, or in the big. When you call a certain method multiple times, that's when you start seeing the gains for the asynchronous I/O stuff. And again, in this specific case, async is about I/O, or overlapping I/O, or using I/O completion ports to be able to better utilize the resources of your system. In this case, your network card and the hardware that pertains to I/O workloads rather than CPU bound. So if you can use the hardware to the best extent possible, then you are going to be able to build scalable systems. And that's what the async I/O capability in C#5 is all about. Asynchronous methods have about 3 times the overhead. Now, don't think I'm saying they are 3 times slower. They just have 3 times the overhead. In other words, the amount of code that is written or generated by the compiler when you write an asynchronous method is about 3 times as much as you would have written, as much as you're seeing, 3 times more than what you're seeing in your own code. By the time the compiler finishes rewriting that code in a specific manner, essentially using a state machine with switch case statements, and I'll show you a sample of that code. So that doesn't mean that the methods are going to run slower. It just means there's a lot of overhead in terms of the amount of code that's written. So maybe your working set will start to go up if you have a lot of async methods as compared to the synchronous versions. But there's lots of performance and benefits to be had. So you have to compare pros and cons, one with the other. You don't want to be using the async I/O capabilities for extremely chatty APIs. It's something you want to test. Performance is never something where you can give somebody a guideline and say this is how you're going to get better performance. As we saw, in fact, in the load test scenarios, on this specific machine that I'm demoing it on, the synchronous version seemed to be far better than the asynchronous version. So that's not to say that's the case in typical production machines, but always test performance. Don't assume something. And always know how to test the performance before you assume that your performance tests are accurately depicting the expected results in production. Okay, so some of the scenarios in which you should or could be using async I/O. So this is the typical scenario where you have an ASP.NET application that is using one or more of these things. You are typically using one or more service calls. So from your main ASP.NET application, you probably would be calling other services that are either SOAP, REST, or just some TCP/IP in other words, async IO being made here, calls being made here. You are calling a database which is also asynchronous. So if you're using in ADO.NET, the core, ADO.NET core, they support the new async IO calls, just like the ADO.NET core has always supported the begin-end APM pattern. They have now enhanced them to support the new async-await pattern. And so if you're making database calls, you can make them using the async IO capabilities in C#5. And if you're making any calls such as to MSMQ or maybe in Azure Service Bus or whatever it is, again, it's all IP or TCP IP, therefore network-based calls. So all of these are network calls, and this is a very typical scenario. And so you should be using the async IO capabilities introduced in C#5. So there's database calls, external service calls, MSMQs, any caching services, maybe in-memory caching, App Fabric, etc. They're all async. They're all IO calls. Therefore, you should be using the async capabilities in C#5. Now, again, I'm not making a blanket statement that you should be using it all the time. It just depends on what's happening. If you need to improve the scalability of this system, then you might want to be looking at making one or more of these calls that you might have in your system asynchronously. There's an impact or a side effect to doing that. We'll look at in a slide that's coming up soon. In some scenarios, so the previous slide was about scenarios that you could use asynchronous capabilities, and here we're talking about some scenarios in which you should not be actually using the asynchronous capabilities, but you should be doing it out of band, meaning it's not even in the same process as ASP.NET. I've seen many people using some functionality whereby they are either spawning a thread or they're doing some long-running operation, and that operation doesn't actually need to be done in your ASP.NET application, but people are doing it. And some of these are things like sending notification emails, logging. Logging actually is a big one. A lot of people just do logging in within this application itself, meaning there's some code here that intercepts every request response and starts to log it in band, meaning within the same request response cycle, if you will. While you should be doing logging out of band, meaning maybe you should be sending a message asynchronously to a queue that actually then is being processed on this side by another application that's doing whatever it needs to do. Even if it's saving it to a hard drive or a database or whatever it may be, it should be done out of band, meaning in by another process. So your main ASP.NET application is just posting a message into, in this case, MSMQ asynchronously. So it's done like in an instant, because it's done asynchronously and it's not waiting for anything to happen. And then another process is then reading the messages in the queue and processing it, and maybe putting it properly in different tables in a database or whatever the case may be. If you're processing any files or documents, moving things around within your ASP.NET application, you might want to see or redesign your system in such a way that these processes, because they're fairly long running. Long running is anything typically 50 milliseconds and longer, and you don't have to kind of wait for the stuff to finish before you proceed. You might want to do this asynchronously. Again, the technique would be the same. You post a message into MSMQ saying, hey, by the way, there's a file sitting in this folder over here, go move it somewhere else, or process it, clean it up, parse it, whatever you want to do, and dump the results in a database or whatever. But the main system does not need to wait till that's done. Even compute-bound work should probably be done out of band, meaning if you're doing any kind of number crunching, again, shoot off a message into a queue, if you will, and move on. You don't necessarily have to wait for the result to come back, and let another process that's listening in on these messages pick it up and do the processing in a separate process. So again, because it's compute bound, you might want to do this work parallelized using threads, but don't use the threads from your ASP.NET application and the app pool that is for this application itself, but use the app pool of another process, if you will. Maybe already on another machine, so you're not even taxing the CPU of the actual ASP.NET web server. The thundering hertz problem. Now, as I said earlier in the few slides, that sometimes, so here I'm trying to show you, this is I-66, which is, if you're in Virginia, you're pretty familiar with what I-66 is, east-west, and this is Route 28 over here, and then this is Route 50. Now at this moment in time, at the time of recording this video, and I'm sure for a few more years at least, there's a lot of work going on Route 50. So there's a lot of work going on over here, road work going on over here. There's a light on 28 over here at the intersection of 66 and 28, which is essentially backing up all this traffic every morning. Luckily, I'm going on the other side of the road. I'm going this way, but I see this for miles, at least a couple of miles, backed up traffic, and it's because there's one light on Route 28. So everyone's getting backed up here on 66. Similarly, everyone's getting backed up here on 50 because of the road work that's going on. So as a result, it looks like Route 28 is perfectly kind of suited for, in terms of the width of the roads and the lights, because traffic just moves smoothly on this road, at least in the mornings, compared to either I-66 or 50. And so Route 28 looks like, going north here, looks like it's handling the traffic load conditions pretty well. That's akin to you having a service that's not doing work asynchronously, therefore threads are being backed up in your IIS thread pool, and then you're making calls from your application, which is your I-66 application, into this application that is the Route 28 application. And so Route 28 application seems to be pretty okay, decently sized to handle the workload that it is currently being issued by both your applications, I-66 application as well as your 50 East application, if you can imagine the metaphors here. So now what would happen if the road work on 50 completed and suddenly Route 28 gets a blast of traffic coming in from 50, which was originally not seen by the Route 28. Similarly, if they fixed the light here on Route 28, you suddenly see a blast of traffic coming in from 66 onto 28. So what then happens is the load of the problem, if you will, the bottleneck now shifts from 66 over here and 50 to now 28. So 28 gets completely choked up. Some traffic residual or backlog is still available or is seen on 50, just like over here on 66. But for the most part, it looks like 66 has cleared up. Same with 50 is cleared up, but 28 is now totally backed up. So this is the thundering herd problem, which is if you have a service that relies, so let's say we have a scenario where we've got a bunch of front-end services. This is the front end. All the requests are coming in from here, from the top. And each of these services relies on, let's say, a few other services that rely on a few other services that rely on some database stuff, right? So typical SOAR sort of architecture here, where each of these is relying on different combinations of services. And if you speed these guys up by using things asynchronously, then the load really gets shifted to these guys. See, it's kind of like 28 was doing just fine. So these servers and services were doing just fine because these services here were slow. Now suddenly you made these services asynchronous. They scale much better, and they basically push all the load down to the services on the next level. And of course, if these are database services and servers, then they get, eventually that's what's happening, is that the tail end, your database servers then get all of the workload, because you've improved the efficiencies or scalabilities of each of these services up the chain. The tail end of it is your database servers, so they're going to see the load. So your database servers really need to be built in terms of the hardware, need to be spec'd out really well in the hardware and hard disks, if you will, so that they can handle all of the pressure that's coming onto them by other applications that now have suddenly become more efficient. So I hope that explains the thundering herd problem, which is a very common problem, especially when you're looking at trying to improve performance. You know, some team maybe that's handling this server here, this service here, you know, gets wise to this new feature in C#5 and starts converting everything into async. That might improve their performance here, and they start loading this box. This box says, whoa, you know, suddenly I'm getting all this traffic from you, what's happening? And I'm not able to handle it. And then they get the wind of this new async capability, and they convert their stuff to be asynchronous, and that starts loading the servers next in line, and that's the thundering herd problem. Okay, so this here in this slide, I want to show you an example of scenarios. This is actually a very I've taken the scenario straight from some code I've written previously from a system where you say in your business layer you're doing this orchestration. You first call the validate file info method, then you have another method that says extract metadata, and so on and so forth. This is the orchestration that something in the business layer is doing, a method in the business layer is doing. And before the async capabilities that we had, we had async capabilities before, as you know, with the begin and other patterns, but now with the async and await, it just makes things, a lot more composable. So, and I want to show you that. So if you identify some of the methods here, you'll see that the extract metadata given a file info is probably async IO, right? Because it's dealing with a file. It probably has to read a file, extract the metadata. So it's a file IO bound workload. Validate using metadata is just compute bound. Since it's once the metadata is in hand, it's probably just looking at the metadata. Create record is database, therefore it's IO bound. Get stakeholders is a database call, so again it's an IO bound call. Send notification is probably an async out of band IO call, but nonetheless from this point of view, it's still an IO bound call, maybe making a call to a message queue service. And then from that point forward, the message queue, the other end of the system is processing the actual notifications, but this is an IO bound call. Process file, again an IO bound call. So in reality, you can see all the check marks here are all IO bound calls. So this method now can be simply written, and I'm going to switch the slide here, just watch the page, to that. So I'm just going to go back. That's what it was before, and it was synchronous, but you can now very easily make it asynchronous. And that is where the composability aspect comes from. So asynchronous is more about the composability of methods. Of course, the method that's calling this method itself has to be, or this method has to be marked asynchronous with the async keyword, async modifier, and then the method that calls it needs to be async and so on. So the whole chain needs to be asynchronous. So if this was somewhere in a controller, let's say an MVC controller, then the action in the MVC controller needs to be marked as asynchronous. That calls into your business layer, this method over here that is marked asynchronous, that's calling into, let's say, like a data layer and other parts of the system that need to be marked asynchronous and so on. And of course, these are the tail end methods that are doing the actual asynchronous IO bound workloads. And so even though this method happens to be in your business layer, it's not the one that's doing the asynchronous work itself, but there are other methods that are eventually doing the actual async work. In this case, for example, the actual database calls in this case and this case are both probably done using ADO.NET Core that supports the composable or the async-await capabilities in C#5. So I just want to give you an example of that, where it's the big benefit of this new async. Try doing this in the begin end await, begin end pattern, the APM pattern, and having multiple asynchronous calls like this. You'd probably not be able to wrap your head around the code that I don't even know how to write the code. I'm just thinking about this stuff and it's like, wow, I don't think I would even want to try it. But now with the async await capabilities, it's pretty simple. So this is the code that is generated by the compiler for a very simple line of code that was written asynchronously. And what you're seeing here on the left hand side is sort of the zoomed in version of the code from here up to probably like about here. I'm not even showing the rest of it. So there's quite a bit more code. That was the sort of the overhead, if you will, I was talking about earlier, where the compiler generated code, there's quite a bit of code, and this is like a typical state machine. You can see here a switch case state machine that the compiler implements for something pretty simple, something like task.start new, factory.start new. So I could show you if you want to see it. So if I were to write the code that generated this code you're seeing over here, it would look something like, let me just write it in line here. So there'll be, say, task, and then you'd have task.factory.start new, and this requires an action. Let's just keep it simple, something like that. So this is a task that returns an integer, as you can see from here. It's a task that returns an integer, right? A simple task like this, and if I had, let's say, this copied, I think I had this copied 3 times, so there's like one that returns a 1, that returns a 2, that returns a 3, and so on. 3 tasks. The code that you're seeing there, it was something like this, basically. It's that simple. And these are tasks, but then you could await them. So you could say value 1 is equal to await task 1, and so on, right? So the code I written was kind of like this. Sorry, this should be value 1 like that. Value 2. Value 3. So it was something like this. And this code generated what we are seeing here in the slides. Okay, so just keep that in mind. Nothing to be scared of. I don't want people to think that you shouldn't be using this because it's 3 times the overhead. It's just something you should be aware of. I mean, so it's not like it's going to be slower. If you can justify the need, then it kind of makes sense. Finally, we're at the last slide of this presentation. We have some references here. One of the references here, the first one, is a blog post I wrote a while back, probably a year or so ago, comparing the APM, the begin-end pair keywords or methods, with the new task-based capability that was introduced in .NET 4.0, where they introduced this task.factory.from async, essentially allowing you to use as parameters to this method the begin method and the end method of something that was previously APM pattern, and you could use them from the task from async pattern. And I did some comparisons there. If you want to check out that blog entry, pretty extensive comparison. Of course, the begin end did win out in terms of performance, but very, very small margin. But compared to the ease of use, again, some of the maintainability and debuggability, if you will, readability of your code base, the performance gain may not be justifiable. Some other links here that I have read over the years that I've accumulated in this slide. A lot of them is about performance, and I didn't touch on p-link. Let me just quickly go just to show you an example. It's parallelized, but for those who have not looked at p-link, you remember this method that we had. I'm just going to delete this stuff here. So this method here that does a from URL and sources, like blah blah. I could also do something like as parallel, and that makes this whole thing parallelized. So it's threaded and it's asynchronous. I'm not saying you should be doing that here, but just a p-link is very, very simple to make things parallelized. And in this specific case, the order or sequence of results is not going to be predictable because it's going to come back with the first one first and so on. But then you can make it predictable by adding as ordered. So as parallel, as ordered would say basically I want them in the same sequence in which the sources have been defined here in the URL thing, right? Again, just want to introduce you. I'm not suggesting you want to use as parallel along with the async in an ASP.NET application, but maybe in other scenarios it sort of makes sense. These are the links that I would suggest you want to look at with regards to any performance testing, scalability testing, especially these two last. These tools have been around for many years. I've used them quite a bit. They're fairly complex to kind of get up and running with. Command line tools that have little documentation, and at this point, if you ask me right off the bat, it'll take me a while to get back into the groove, but they're useful tools and have been around for many years, and are part of the IIS SDK, if I'm not mistaken, available from IIS.NET, if you can see the URL here. So if you are going into performance testing or load testing of large systems, besides the tools that come in Visual Studio, you might want to look at the WCAT tools as well that are available here in these two links. There's x86 version and x64 version. That's the difference in the two links here. So that's it. I hope you have enjoyed watching these two parts, and that I have done a good job of trying to explain things to you with regards to the new async-await capabilities in C#5. Thank you and have a good day.